Welcome back to the UAV Understanding Drone course. In this lecture, we learn about the sensors used in designing drones. Now, sensors are also included in the component section, but there are so many sensors used that one lecture is not enough to explain everything. As the name suggests, a sensor is a device that detects changes in electrical, physical, or other quantities and thereby produces an output as an acknowledgement of the change in the quantity. Mostly, this output is in the form of an electrical or optical signal. Drones use sensors to monitor current situations so that they can react efficiently, such as taking high quality visuals, enabling the delivery of the right supplements to the right location. Small drones have evolved from toys to controllable aircraft capable of carrying cameras for photo survey, surveillance, and broadcast applications. One of the key factors in this improvement has been the use of high performance micro electromechanical systems, that is MEMS sensors. There are basically three categories of sensors used: inertial measurement unit, GPS or GNSS, light detection and ranging, that is LIDAR. Let us begin with the inertial measurement unit. The inertial measurement unit, known as the IMU, is an electronic sensor that measures the velocity, orientation, and gravitational forces. This sensor owes its development to the evolution in MEMS micro electromechanical systems, which in the 1990s saw the emergence of the first commercial products. It is the main component of inertial navigation systems and maneuvers in the UAV systems. It uses a combination of accelerometers and gyroscopes to accurately estimate UAV's attitudes, including rolls and pitch. It also uses magnetometers, a supplement of accelerometer and gyroscope, to measure the heading, that is yaw, and to measure and report a drone's specific force, angular rate, and the magnetic field surrounding the drone. The accelerometer determines the linear movement along any axis, that is, it measures acceleration in all the three axes. There are a couple of accelerometer types that function in different ways, but most accelerometers rely on the piezoelectric effect. The main working principle of an accelerometer is that it converts mechanical energy into electrical energy. The force caused by the vibration or a change in motion causes the mass to squeeze the piezoelectric material, which produces an electric charge that is proportional to the force exerted upon it. Gyroscope determines the rate of rotation, or you can say angular velocity and tilt. It measures angular rate in all the three axes. It is called a vibrating structure because when rotating the gyroscope on an axis by the Coriolis effect, a vibration is produced that is measured by capacitive plates. The signal generated by the plates is treated to be proportional to the angular velocity. There are two fundamental characteristics of a gyroscope: gyroscopic inertia and precision. Firstly, gyroscopic inertia. If the rotating body is mounted and freely moves about an axis that passes through the center of the mass, then the spin axis will remain fixed in inertial space without displacing any of the frames. The second one is the precision. Suppose the body is rotating in x direction and a force is applied in y direction. Then the body will not start rotating in the direction of the applied force, but it will rotate in the resultant direction between the x and y axis. Gyroscopes determine the rate of rotation, degree of tilt, and angular velocity of a moving object. MEMS-type gyroscopes are commonly affected by various sources of error. The most common one appears when the gyro presents a measurement different from zero even though it is immobile. This error influences the calculation of the angles of inclination through methods of numerical integration. This factor can be corrected by determining the offset present in the measurement over an extended period of time in a still state. The gyroscopes alone cannot provide a perfect measure of the rotational movements of a UAV. as they are commonly affected by external noise and tend to drift continuously. Therefore, it is necessary to incorporate magnetometers and accelerometers. All of these measurements are fused together with information from different sensors to provide measurements that can be used to calculate the orientation, pressure altimeter, and velocity of the UAV. A barometer is used to measure atmospheric pressure and calculate the drone's altitude. It can detect if the drones move a few centimeters, while a GPS receiver is mainly used to determine the horizontal position of the drone. While both barometer and GPS are capable of measuring height, they are based on different algorithms. Magnetometers indicate the direction of the magnetic field to verify heading. Using a magnetometer on a drone enables us to scan the area and detect metals several times faster compared with handheld devices and allows obtaining geo-referenced maps of the area. They have superior accuracy and response time characteristics while consuming significantly less power than alternative technologies. They are very well suited for drone applications. This sensor is based on the Hall effect, although it is not the only one. The Hall effect on these sensors can be described as a situation in which a current carrying semiconductor is placed in a magnetic field. The semiconductor load carriers will experience a force perpendicular to the magnetic field and current. At equilibrium, a voltage will be created between the corners of the semiconductor.